All right, so we are going to look at the problem, two thrown stones. I'm not going to do all the math. There's a significant amount of math, but I am going to look at the physics of it and see if we can get to the point where we could bring this problem down to one unknown, because I think that's one of the biggest problems with this problem. We have two balls, they're thrown up in the air, and I'm just going to pick an initial velocity, and both of them have the same initial velocity, whatever it is, right? So I'm going to say that they both have an initial velocity of 25 meters per second. And we also know that the balls are thrown at two different times. Ball one is thrown up in the air, ball two is thrown sometime later. So for me, I'm going to say that the first one, time one, the time for the first stone is, we'll say, a second before the other one. So time one equals time two plus 1 second, right? Because stone two was thrown up later. How much later? Well, again, you have your own number, but I'll say that stone two was thrown up 1 second later. So if stone two was in the air for 2 seconds, well, stone one was in the air for 3 seconds, right? There's a difference of 1 second. So the question is, and really we're just going to focus on the first one, because you get the first one right, you should be able to do the other parts, because now you have a lot of information. But the question is, at what height do they cross each other? Stone one is thrown up in the air with a speed of 25 meters per second. A second later, stone two is thrown up in the air with the same velocity, 25 meters per second. At what height do they cross each other? So first of all, there's only one way where they can cross each other, right? Stone two goes up, reaches a high point, comes back down. Stone two is going to do the exact same thing. It's going to go up, it's going to reach a high point. It's the same high point because it's leaving at the same speed, and it's also going to come back down. So how can they both be at the same height if stone two is thrown after stone one? Well, the only way possible is if stone one is on its way down and stone two is still going up. Sorry, that should have been a down arrow there, right? It's going up and it's coming down. Sorry. Just like this one. So the only way that this could be possible is if stone one is on its way down and stone two is still on its way up. So all of this doesn't really matter. This would be after they are at the same height. And for this one, all of this doesn't really matter, because this is also after the point that I care about. So I care about when they're at the same height. And whatever that height is, this is the only way it could be, is one's coming down, the other one's going up. And I'm going to say, there we go. And I'm going to say I am looking for this, which is my height, or this is my displacement. So I know they both have the same displacement. Even though one's going down, even though one's going up, they're at the same displacement. So what do I know? Well, for stone one, again, there's 5 things I could know. I could know the initial velocity, the final velocity, the acceleration, the time, and the displacement. Well, I know I don't know the displacement. That's one of the things that they don't tell me. This would be a real easy problem if they told me that. I know I don't know the time, because that's what we're looking for, the time that they're at the same height. I know the acceleration. It's free fall, negative 9.8 meters per second squared. I don't know my final velocity. That's, again, another piece of information we're looking for, but I do know my initial velocity, 25 meters per second. I look at stone two, and just to save us some time, I know all the same things. I know that its initial velocity is 25 meters per second. I don't know its final velocity, though we'll talk about these things in a second. I know my acceleration, because it's also in free fall, negative 9.8 meters per second squared. I don't know my time, and I don't know my displacement. I'm going to add some stuff to this, or at least talk about some things. Now, what do I know? Well, I know these two velocities. One's up, one's down. I know the magnitude of these velocities has to be the same, right? We talked about this in class. Sure, this one's going down and this one's going up, because they both have the same acceleration, and they both have the same initial velocity. Then when this one's going down and this one's going up, they're both at the same speed. They have to be at the same speed, if you remember what we talked about before. And if you don't, then go look at the problems we did before this. So yes, they're different velocities. They're exact opposites of velocities. This would be a negative velocity. This would be a positive velocity, but the number would be exactly the same. So I know that. That's something I know about this situation. I don't know my times, but I'm going to call this one time one, the time for the red stone to be up in the air. And that's going to be a longer time. And this is time two. This is the time for the blue one to be in there, and that's going to be a shorter time, right? But I have a relationship between these two times, right? They are different by 1 second. So if I know one, I can get the other, whichever one I solve for. I also don't know the displacement, but I do know the displacements are exactly equal to each other, because displacement is a straight line length from point A to point B, so to the ground to where it hits. They're not, they're both positive and they're both the same. So they're exactly the same as each other. So that's useful information. So I know the displacement equation over here, it's going to be something, I'll write it up here. First of all, I'll write my displacement equation. There it is. And then I'll write my displacement equation for stone number 1. Well, it's going to be 23 meters per second. 25 meters per second times time 1, the time for stone 1 to get to this point, plus 1/2 negative 9.8. So I'm going to say negative 4.9 meters per second squared times time 1 squared. And that equals the displacement for stone 1. Well, the displacement for stone 2 is exactly the same. It has an initial velocity, 25 meters per second. I shouldn't say exactly the same. There's one difference, and that's the time. Stone 2 is not in the air for as long. It has a different time because we threw it later, and it's still on its way up while 1 is coming down. Plus, well, it's still 1/2 of negative 9.8, so it works out to be 4.9 meters per second squared times the time for stone 2, which is time 2, squared. Now, what do I know about these two displacements? Well, I know they have exactly, well, these two equations, I know they have exactly the same displacement, so I can just let them equal to each other. And that's helpful because I'm getting rid of one thing I don't know, right? I'm starting to write an equation where I'm getting rid of some of the unknowns. So final velocity is not in the equation. Great. Displacement, no longer in the equation. Great. Yes, this was equal to displacement, and this was equal to displacement. By setting them equal to each other, I don't know what the displacement is, and I don't care what the displacement is to a certain extent, because now I'm starting to get something that's different. Now, I still have two unknowns. This is time 1, the time for stone 1 to go all the way up and start coming back down. This is time 2, the time for this one just to go up. So again, I know I keep saying it, but they're different times. So I have one equation, but that equation has two unknowns. But I know this. I know the relationship between the two of them. So I like it the way it is. Even though I understand I'm solving for time 2, the shorter time, I can take this value and I could substitute it there, and I could substitute it there. So what will this side of the equation look like? This side will look like 25 meters per second times time 1, but now it's going to be times 2 plus 1 second, plus a negative, so minus, I'll leave it plus a negative. And actually, give me 1 second. Keep my color coding the same. There we go. Plus a negative 4.9 meters per second squared. And then it's time 1 squared. Well, time 1 equals times 2 plus 1 second. Now, I like unit analysis, but this is one case I think I would not do unit analysis because it just gets hairy, really hairy. Times 2 plus 1 second squared, and that equals, and I didn't change anything on the right side because it's already in terms of time 2, so it's 25 meters per second time 2 plus a negative 4.9 meters per second squared time 2 squared. So now I have this equation, and I'm not saying it's a beautiful equation. It's actually a pretty rough equation that I'm going to leave for you to solve. But I will say I have an equation based on my understanding of what's going on and what's related to what and how they're related. I have an equation with just one unknown. When I solve this, the only thing I don't know is times 2, right? Time 2 is everywhere in the equation. So yeah, I've got some work to do to get it by itself and to solve for time 2. But it's the only unknown. So now it's just a question of, do I have the algebra skills to go ahead and solve this problem? And that's where you have to do things. And this is definitely one of those questions where everything you ever learn in algebra pops up. The only thing that I don't see in this equation is the quadratic equation, but that showed up in other homework problems, or at least one other homework problem, right? But everything else shows up here. I have to distribute the 25 meters per second here and here. I've got t plus 1 over here, and I've got to square that. So I've got to FOIL that, right? So it's t plus 1 times t plus 1. I got to use the FOIL method, first, inside, outside, last, and I got to simplify. Then I got to distribute the 4.9 into all of that. So this is where I'm saying units still have to work, but it gets a little ugly, so I might just drop the units and just solve stuff. I will say two things, though. If you do it right, it simplifies fairly well, and it does that because they both have the same initial velocity, and they both have the same acceleration, and that makes this a neater problem. So once you do the math on the left side correctly, you'll see that it just cancels out some of the stuff on the right side. So it actually cleans up okay. The other thing to point out is in this problem, I'm solving for time 2. The way I set it up, I'm solving for time 2, which is not the time the question's asking for. The question's asking for starting from the start of this problem. Well, when did this problem start? It started when I threw this one in the air. So when I solve for T2, I have to go back and plug it in and solve for T1. Now, you could have did your substitution differently. You could say, well, T2 equals T1 minus a second, and plug in on this side and do a different substitution. I just like the way I do it, right? So there's other ways to do this problem. This is the way that works for me. When I solve for the time in this equation, I understand it's not the time I'm looking for. It's the shorter of the two times, and the question's asking for the longer time. So that's everything in a nutshell. That is how I would do this problem. Now, once I get the time, to be honest with you, once I get either time, this problem becomes immensely easier. Because once I know one time, I can get the other time. So that makes that easier. And regardless of which time I know, I can now plug it into either one side, the red side or the blue side, either time, and I could still get this height. I can get this displacement. So it doesn't really matter what I use. And then when it asks for the speed at this point, well, guess what I could do? I could still use either one, because guess what they both have? They both have the same speed. So even if the problem designates what's the speed of the one going up, well, it doesn't matter if you solve for the one going up, because guess what? The one coming down has the exact same speed. So once you get a time that's correct, you really can't go wrong on the rest of the questions, even if you use the wrong time, right? Even if you're like, oh, I used T2 instead of T1, doesn't really matter for the rest of the questions. It only matters for the first question when it specifically asks for one of these times. Everything else works regardless of which one you do, because they both go to the same displacement. They both have the same speed at that displacement. Okay, so this was Two Thrown Stones, quick and dirty. You still have to do all the math, but I think this gets us set up where you should be able to do the math.